Hello everyone. Today I'm going to talk about using Apache Pulsar as a modern, scalable, high-performing JMS platform. My name is Yabing Man, and I am a Vanguard Solutions Architect at DataStax. I'm going to start today's session with the introduction of JMS and Pulsar. Then I will take a deep dive into DataStax Starlight API for JMS. This is the key part that enables using Apache Pulsar as a native JMS provider. I will conclude today's session with a summary. The acronym JMS comes from Java Messaging Service. This name has been rebranded under Jakarta Messaging a few years back as part of Jakarta Enterprise Edition. JMS is a generic Java API for message-oriented middleware, which makes possible of asynchronous message exchange among different systems in a standard way. JMS is a relatively old technology which was created in 1998. Over the years, JMS has slowly progressed into different versions up to the latest version 3.0, which was released a little bit more than 1 year ago. In JMS, there are two major messaging domains. The first one is point-to-point or P2P. In this messaging domain, messages are sent to a queue by senders. Each message in the queue will be delivered to one and only one receiver. There is no timing dependency between a receiver and a sender. This means that the receiver is able to receive all the messages in the queue, even for those messages that are published to the queue before the receiver connects to the queue. The second messaging domain is publish subscribe or PubSub. In this domain, messages are published to a topic by publishers. Each topic can have multiple subscribers. Each message in the topic will be delivered to all active subscribers at the same time. There does have a timing dependency between a subscriber and a publisher. This means that a subscriber can only receive the messages in the topic that will publish to the topic after the subscriber connects to the topic. If a subscriber is offline and then comes back online, the subscriber is not able to receive those messages that were published to the topic while it was offline. JMS API also evolves over the years. The initial version 1.0 API is a domain-specific API. This means that there are two sets of APIs, each for one messaging domain. Version 1.1 API consolidates the domain-specific API into one single API suite. This is also called Classic API. Version 2.0 API makes further improvements and simplification on top of the Classic API and is therefore called Simplified API. Version 3.0 API has no major changes other than some implementation detail improvements. JMS API is a simple and straightforward API. There are not many objects involved in the API. The two diagrams on the right side shows the main JMS objects and their relationships in the Classic API and the Simplified API. JMS is an API and a specification and is not an actual implementation. The actual implementation is done by different vendors as different JMS providers. The implementation details regarding connecting to the providers and getting the destinations are different from provider to provider. So in order to maximize the JMS client application portability, it is always recommended to put the implementation specific JMS objects in the JNDI namespace. These objects are connection factory and destination. So when the JMS client's application tries to connect to a JMS provider, instead of connecting to the provider directly, it first does a lookup to the JNDI namespace to get a connection at the destination. After that, the JMS code is standard and can be reused from provider to provider. Introduction of Pulsar. Although JMS has played a critical role in the past decade regarding enterprise message processing, it is a no technology, and nowadays it becomes more and more unable to meet the requirements and the challenges that are faced by a modern data application. Some of these challenges come from functional requirements perspective, such as to be able to do real-time advanced event processing. Other challenges come from critical non-functional requirements perspective, such as high availability, always on, low impact disaster recovery, and horizontal scalability. Simply speaking, Apache Pulsar is a cloud-native, distributed, and unified messaging and streaming platform. It is a technology that is similar to Apache Kafka, but is relatively new. Apache Pulsar was originally developed in Yahoo and open sourced in August 2016. It became an Apache incubator project in August 2017 and a top-level project in October 2018. Ever since then, Apache Pulsar has gained a lot of attention from the industry and the community, and it grows very fast. The three diagrams on the right side shows clearly how fast Apache Pulsar has grown in the last 3 years. It is worthy to mention that since last year, the number of monthly active contributors to Apache Pulsar project has outnumbered that to Apache Kafka project. Although Apache Pulsar shares some similarities with Kafka, but what makes Apache Pulsar unique? Why would we use it? In my opinion, there are 4 key differentiators that brings unique advantages to Pulsar over Kafka. The first one is a tiered architecture design, which is summarized in the diagram on the right side. By this design, a Pulsar producer or consumer interacts with a broker for message processing. Unlike in Kafka, the Pulsar broker is stateless, which means that the broker does not handle message persistence. Instead, the message persistence is handled at a different layer by Apache Bookkeeper, or Bookies as in this diagram. Apache Bookkeeper is a dedicated distributed log management system that is extremely efficient. I'm not going to jump into the details of this tiered architecture design of Pulsar in this session. All I want to point out is that this architecture design has several obvious benefits compared with Kafka. The first benefit is that through the separation of the computing layer and the storage layer, we can actually scale, manage, and tune these layers separately according to our actual workload. Either it is a CPU intensive or disk IO intensive. The second benefit is that this tiered architecture design guarantees a more balanced and a more efficient resource utilization. It also achieves a true horizontal scalability. The third benefit is that this architecture design guarantees that the Pulsar cluster to be able to scale in a much faster fashion and at the same time have a lot less impact to the existing applications. These are the 3 areas that a Kafka cluster is struggling, especially in a large deployment. The second key differentiator of Pulsar is that it has a unified and flexible messaging model, which makes Pulsar fully capable of handling both the queuing use case and the PubSub use case. While we are looking at the Kafka, it is always a little bit challenging to deal with the queuing use case, which is still very common in many large enterprises. The third benefit of having Pulsar is that it has a native geo-replication capability. With a simple configuration, a message published into a Pulsar topic can be seamlessly replicated to different data centers in different regions. There is no need to rely on external third-party utilities or tools or ETL processes. The last but not least is that the Pulsar is a true robust multi-tenant system. The tenant is at the core of the Pulsar messaging processing model and is a first-class citizen. In Pulsar, messages are organized in a hierarchy structure starting from a tenant. One tenant is an organization unit, such as a department or a company. One tenant may have multiple namespaces. One namespace is used for convenience purposes to manage a set of topics that share a similar security or resource utilization policies. When these policies are applied at the namespace level, they will be applied to all the topics within the namespace. But you can override the namespace policy by setting the policy directly on an individual topic. Messages are published to a topic by producers and consumed by consumers through subscription. In Pulsar, subscription can have types. When comparing with Kafka, the consumer group-based Kafka message consumption is roughly corresponding to the shared subscription type. The other Pulsar subscription types can be used to address messaging processing use cases where it can be a little bit challenging in Kafka. Pulsar messages can have different types, whether it's primitive types or complex types such as Apache Avro. The message types are managed through a built-in full functional schema registry. Now comes to the major part of this session, DataStax Starlight API for JMS. The DataStax Starlight API is a set of APIs. It includes the API for JMS, which is the focus of this session, the API for Kafka, and the API for RabbitMQ. But what is really about it? Why do we need it? In order to better understand it, we need to talk about why we think of Pulsar as a unified platform. In my opinion, there are 4 different aspects of it. The first one is Pulsar is a unified platform for both the messaging and the streaming use case. The second one is Pulsar is a unified platform for both the queuing and PubSub use case. The third one is Pulsar is a unified platform across many different infrastructure environments, including on-premise, hybrid clouds, and multi-clouds. The last one is Pulsar is a unified platform that can be used with many existing messaging protocols, such as JMS, Kafka, and RabbitMQ. That is what the Starlight API suite is for. Through the Starlight API suite, applications following the existing messaging protocols can interact with Pulsar natively without much code change. The Starlight API for JMS is fully compatible with JMS 2.0 API, which is backward compatible with JMS 1.1 API, and it is fully open source. Using the Starlight JMS API has many benefits as listed in this page. To summarize, through this API, existing JMS applications with very minimal code changes are able to utilize Apache Pulsar as a native JMS provider that is highly available with horizontal scalability, having blazing fast performance with much simplified operation complexity. The total cost of ownership is therefore greatly reduced. This API maps the main JMS objects to the corresponding Pulsar objects. This mapping is very straightforward, and we are not going to read them line by line. One thing to notice here is in Pulsar, there is no concept of temporary topic. So the JMS temporary destination is also mapped to a persistent Pulsar topic. But the API is taking care of the temporary behavior, as we are going to explore a little bit more in future slides. This is an example code of using this API to create a JMS queue, producing messages to it, and consuming messages from it. This simple program follows a typical JMS program workflow, starting with creating a connection to a JMS provider, which is Pulsar here, setting up a JMS context, creating destination, creating producer and consumer. The only codes that need to be changed are those marked by the red lines. These codes are related with the JMS administrated objects, which are connection factory and the destinations. All other codes are standard and don't need to change. Jumping into the details, the first step is to create the connection to the JMS provider, which is a Pulsar cluster. This is achieved by the Pulsar connection factory object in this API. This object has implementations to both JMS 1.1 and 2.0 specification. Behind the scene, this object maintains the actual connection to the Pulsar cluster through the native Pulsar client libraries. In order to properly set up the connection, there are a set of connection properties that need to be provided. Some of them are mandatory, such as the service URLs and the security-related features. There are a set of properties starting with the prefix JMS dot. These are the properties that can impact the API behavior. We are going to talk about this one such property of JMS.system namespace with more details in the next slide. Once we have the connection, we can create JMS destinations. As we mentioned earlier, JMS destinations are mapped to Pulsar persistent topics, no matter if it is a regular destination or a temporary one. The difference here is that for regular destination, the client application needs to provide a topic name string. If the provided topic name string does not have tenant and namespace within it, then it needs to be created under a default tenant and namespace. The default tenant and namespace is specified by the JMS.system namespace connection property, as we mentioned in the previous slide. For the temporary destination, the Pulsar topic name is randomly created under the default tenant and namespace. Since Pulsar has no temporary topics, the Pulsar topic that is created for the temporary destinations needs to be explicitly deleted when JMS connection is closed. From the connection, we can create a JMS producer and a consumer. This is straightforward. Both a synchronous API and asynchronous API are supported. From the connection, we can also create queue browser. This is achieved by Pulsar Reader API behind the scene. From the queue browser, we can pick a message in the queue without deleting it. Now comes to the message itself. In JMS and Pulsar, the message structures are a little bit different. In JMS, one message can have headers, properties, and a body. In Pulsar, a message can have a key, properties, and a body. So the mapping from a JMS message to a Pulsar message is a little bit more involved. For JMS headers, they are generally mapped to Pulsar properties. But normally, JMS headers have special meanings, and these special meanings may not be respected by Pulsar natively. So the Starlight API actually simulates these behaviors. For JMS properties, it depends on the situation. For application-specific JMS properties, they will be mapped to Pulsar properties on one-to-one basis. For standard JMS properties, most of them are ignored, but there are few that have special treatments. For example, for JMS X group ID property, if it is specified, it will be translated into Pulsar message key. For any vendor-specific property, it is not supported because this API only supports the standard specification. But if your application depends on this vendor-specific property, we'd like to talk with you and figure out a way how to migrate. The API also adds two special properties. These are not standard JMS properties and will be only used by this API. JMS message body may have different types, such as a stream message, map message, and etc. All these types are supported in this API. Behind the scene, these types are mapped to Pulsar byte array message type, which is the default message type in Pulsar. The message type itself is recorded in the JMS Pulsar message type property, as we seen in the previous slide. This property will be used to properly serialize and deserialize the byte array. All JMS session modes are supported, including various JMS message acknowledgement methods, as well as a JMS transaction. For the different JMS message acknowledgement methods, they are all achieved by the same Pulsar message acknowledgement mechanism. The only difference here is that whether a synchronous Pulsar acknowledgement is used or an asynchronous Pulsar acknowledgement is used. For example, in the auto-acknowledge method, a synchronous Pulsar message acknowledgement is used. So just be aware of this performance difference here. JMS transaction is also supported. It is mapped to Pulsar's own transaction, which allows atomic multi-topic writes and atomic multi-subscription acknowledgement. In order to use JMS transaction in this API, we need to do two things when we create the connection. The first thing is we need to specify the enable transaction connection property to be true. The second thing, we need to specify the session mode as session transacted. Be aware that in order to use a JMS transaction, the Pulsar version needs to be at least 2.7.0. If you want to achieve exactly one semantics in the transaction, then the Pulsar version needs to be at least 2.8.1. Delayed message delivery is a common request in JMS. Although it is not a part of a JMS spec, because of its popularity, this API also implements it. All we need to do is to call producer's set delivery delay method, which will be translated into Pulsar's native method. Message selector is another common request in JMS. Currently in Pulsar, there is no native support for it. Although similar functionality can be achieved through Pulsar function programming, it is a little bit more involved than necessary for this purpose. There's already a proposal to add this feature in Pulsar. Likely it will be available in version 2.10. The Starlight API also simulates this behavior. Basically, the API will receive every message from the topic and check if it meets the message selection criteria. If it meets the criteria, the API will receive the message and move on. Otherwise, the API will do a negative acknowledgement, so the message will stay in the topic. As we've already seen from the previous slides, not all JMS features are relevant or natively supported in Apache Pulsar. But the Starlight JMS API simulates most of them, such as message selector, as we've just seen from the previous slide, per message TTL, message priority, and so on and so forth. For more details, please refer to the documentation. For security, the Starlight JMS API completely relays the control to Pulsar, which has a much more advanced security feature than JMS, which includes pluggable authentication, authorization, transportation encryption, end-to-end message encryption. The OpenID integration, such as with the Keycloak server, is also possible. Right now, it is available with the DataStax Apache Pulsar offering called Luna Streaming, but it will be available in the mainstream open source Apache Pulsar as well. The Starlight JMS API can be created as a resource adapter as a part of the Jakarta EE environment. By deploying this resource adapter in this environment, it allows the enterprise message beans to be able to talk with the Apache Pulsar natively. This API also includes a simple implementation for JNDI integration, which allows it to retrieve JMS connection factory object and destination object through JNDI lookup. Please note that this implementation is a dummy implementation at the moment. It has not integrated with any actual JNDI service providers yet, such as LDAP. This can be improved in the future. To summarize, JMS has played a critical role in the past decade as an enterprise messaging technology and is still used by many large enterprises. But it becomes outdated and faces many challenges. Apache Pulsar is the replacing technology, which is a unified messaging and streaming platform with many unique benefits. The Starlight API allows existing JMS applications to be seamlessly migrated to Apache Pulsar as a native JMS provider with very low impact. Here are some resources that you can reference to, including the GitHub repo, DataStax documentation, blog post, and some sample codes. Thanks for watching.